All right, guys, we're going to take a look at analytically finding the derivative of polynomial, things that kind of resemble polynomials, and then sine and cosine functions. So before we even begin that, though, let's take a look at the bell word quick. So if you haven't done it yet, please pause it and give it a try on your own, okay? All right, so hopefully you went and did that. Of the two graphs pictured to the right, explain which of these is f of x and which is the derivative. So hopefully you remember our little trick where we figured out that the derivative always went down by 1 degree. So that would be why this one here is clearly the derivative. And to kind of answer that, of course, that would mean that the derivative, whoops, can't spell. Wow, I really can't spell. The derivative of polynomial functions always have a degree of 1 less than the original. All right, now the next one is a little bit trickier for sure, but hopefully you can still kind of figure it out here. This is really just like two functions, and so this one would be my g of x, and this one would be g prime, because in an absolute value function we have two distinct slopes that change at the vertex. And here we can see exactly that. Here my slope is clearly +1, here it is clearly -1, and we see that reflected. So it's the same sort of idea, but yeah, really like you're just looking at the two slopes of them to be able to tell which one's which. All right, so let's actually jump into this then for real here. So consider the function f of x equals 3. What does the graph of that function look like? If a tangent line were drawn to f of x of any value of x, what would the slope of that tangent line be? Well, the graph of like this is literally just sort of the idea of y equals 3. So it would, if this was our Cartesian plane, it would literally just be here at 3, right? And so the slope of a horizontal line is, of course, 0, which we talked about last class as well. So based on this thought process, if f of x equals c, where c is a constant, then the f prime of x is going to be 0 because it's just a flat line. That's all it is. Okay? Now, shown below, we've got 6 different polynomials or polynomial-like functions. I'll talk about that when we get there. And watch, I'm going to find the derivative here, and we're going to see if you can kind of figure out the pattern. So, f prime of x of this guy here is 6x minus 2. F prime of x on this guy is negative 15x squared plus 4x minus 3. Next one here, it's going to be negative 9x squared plus 24x cubed. F prime of x on this one is going to be 2x to the negative 2 minus 6x to the negative 3. Then we're getting into the really tricky ones. F prime of x is going to be 4x to the negative 1/3 minus 8x to the negative 3. And our last one here, f prime of x is going to be equal to 3x to the negative 3/2 plus 3/2 x to the negative 1/2. Now, hopefully you started to figure out the pattern. I find usually students start to get it by about the third or fourth one. Some of you have already figured out this pattern, and so it's like nothing new for you at all, really. And what it is what we learned is that the derivative of a power, right, which we're going to call the power rule for differentiation, is literally just that the number up in here, the exponent, comes down in front, and then we subtract 1 from that exponent, right? So if we go and look at a couple of these, right, up here, the 2 came down, multiplied by the 3 to give me 6x. 2 minus 1 is 1, so 6x. Okay? When we look at this one, there is a 1 here, so the 1 came down to give me negative 2, x to the power of 1 minus 1. Well, x to the power of 0 is just 1, so the x goes away entirely. Now, if we look down here where they're polynomial-like, I say polynomial-like because technically polynomials have to have integers, whole number exponents, and these of course have negatives or fractions, but we call them polynomial-like because they act the same way. So This negative 1 came down, gave me positive 2, and then I subtracted 1 to give me x to the negative 2. And so either way here, yeah, like we're getting, this same pattern over and over again. We do a fraction, same thing. 2/3 times 6 is just going to be 4, and then x to the 2/3 minus 1 is negative 1/3. All right, so let's take a look at this and see if we can kind of apply this a little bit here. So, in order to apply the power rule for differentiation, the equation must be written in polynomial form. And as we kind of already talked about that, it's really just the sum and difference of monomial-like terms, okay? And here it's like monomials that can have negative or fractional exponents. So that's like our different by making it polynomial-like, okay? Now let's go ahead and apply this a little bit here. And in order to do that, we're going to need to kind of rearrange these sometimes to make it easier. Because, for instance, we don't know how to take the derivative of something when it's on the bottom. But we can rewrite f of x using negative exponents. So we could change this equation to be this instead. And once we've done that, then we can find the derivative. Because now the negative 2 comes down to give us negative 4x to the negative 3 minus 12x squared. All right. Now, when we get something like this one over here, this one is also going to be similar where we're going to rewrite it by pulling out that common factor of x from the top so that we can cancel it out. Because then we're going to get 3x cubed minus 3x minus 2 all over x, and those x's can now be canceled. Now it looks like a polynomial or actually it is a polynomial in this case, and so it would be 9x squared minus 3. All right. Now, on this next one, we got to do a little bit of legwork first here until we learn some other rules. So we're going to need to multiply these things together. And so f of x in this case, we're going to multiply these first two together, which is x squared plus 2 plus 3, so plus 5x, and then plus 6. And then we're going to need to multiply that whole thing by 2x plus 1. So then we just got to go ahead and multiply 2x through the whole thing, which will be 2x cubed plus 10x squared plus 12x. And then we multiply 1 through the whole thing, so plus x squared plus 5x plus 6. And then, of course, combine your like terms. And so let's see, we got only the 2x cubed, but we can combine the x squareds here to give me plus 11x squared. We can combine the x's to give me plus 17x, and then plus 6. Once I've now got it into that polynomial form, I can find the derivative nice and easy. So 6x squared, because again, the 3 just comes down, subtract 1. 2 comes down, so plus 22x, and then plus 17. So the key here is really like the legwork is making it look like a polynomial-like function. Once we've done that, it's super easy. So this one is going to be very similar, where I can rewrite this as being kind of splitting apart that common denominator and writing it as two separate fractions before we did the combined denominator, which we've talked about before. And then I'm going to simplify those. And so that x cubed over x to the 5th is really the same as x to the negative 2. And again, I want it this way, not as a fraction, because I need to be able to actually do the power rule after. And then 5x squared over x to the 5th is going to be 5x to the negative 3. Now that I've got it looking like a polynomial, we can go ahead and do it. So negative 2 comes down, so negative 2x. Subtract 1, we get minus 3. Negative 3 times negative 5 gives me positive 15. Subtract 1 from that negative 3, and we get minus 4. So like I said, I think you're starting to really get the idea here. Not too hard, not too bad. We're just doing the same process. All right. So here, don't panic, right? But think about this. Let's first try and rewrite this bottom part here with a fractional exponent. So that would be to the 2/3. Then, of course, I can simplify that, because this is like x to the 1 over x to the 2/3, which is 3x to the 1/3. And then, of course, f prime. Now, if you're having a hard time with that simplification part, guys, I mean, that's all pre-calc, so try to review some of that. Maybe come and get some extra help if you need it. But that's the pre-calc stuff. The pre-calc is the part where we make it look like something we can do, and then we just take the derivative. So the 1/3 comes down, times 3 gives me 1, and then we subtract 1 from 1/3, and that gives me negative 2/3, okay? Now, after that point, you can write it however you want. You can then put it back into a fraction, put it into roots. Doesn't matter, but I like to just leave it in the fractional form. All right, over here, there's actually nothing to do. We don't need to convert anything. We just need to actually do the question. So f prime of x, the 3/4 come down and multiplied by 4. So I'm going to write this one out kind of the long way for you, just in case, and just to kind of reiterate that this is what's going on. X to the 3/4 minus 1 would be negative 1/4. Plus 2 times 1/4. I'm doing this partially just because these are awkward fractions, right? And so if you're having a hard time with it, go ahead and write it out this way first. And then 1/4 minus 1 would be negative 3/4. Then simplify your fractions. So negative 4 times 3/4 there is just going to be negative 3. 2 times 1/4 is just going to be a half. And there we go. Now we are done. I should have written that this is f prime of x. There we go. So hopefully that kind of makes some sense there. Yeah, I mean, we can obviously rewrite this with like non-fractional exponents. We can rewrite it with non-negative exponents, but well, let's do it just for the one, I guess, just to practice it. So we could also write this as like f prime of x is equal to negative 3 over x to the 1/4 plus 1 over 2 x to the positive 3/4. Or we can even go another step further and write them with those roots. So it's going to be negative 3 and the 4th root of x plus 1 over 2, and again the 4th root of x, but it's of x cubed this time. So any of these are all correct. All right, now, I already know that most of you don't remember your trigonometric identities, so let's go ahead and look at the sum identities here. So if we have cosine of a plus b, that is the same as cosine of a times the cosine of b minus sine of a sine of b. Now, allegedly, you should have learned about these already, but if not, here they are. And if you did, it's just a refresher. Now for sine, it's similar, but this one's going to be sine of a cosine of b plus sine of b cosine of a. All right. Now we're going to use that in order to be able to kind of find some of our trigonometric ones here. All right. So using the limit as h approaches 0 of this to find f prime of x in each of the following situations. So we only really need to do one of these, but we'll do them both, I guess, quickly. So this here, this would be that the limit as h approaches 0 of sine of x plus h minus sine x all over h. Then we're going to have to use that identity that we just did up here, so that's this guy. And so this would be sine of x cosine of h plus sine of h cosine of x minus sine of x all over h. And let's see. From there, what can we pull out? I'm going to rearrange the way that's written a little bit. So I'm going to move this sine x over here so that I can pull out a common factor. So I'm going to write it as like sine of x cosine of h minus sine of x plus sine of h cosine of x all over h. Because then I can pull out that sine. So So sine of x, this is going to be cosine h minus 1. All right. And then that's because we pulled out the sine x here. And then this part doesn't change. So sine h cos x, oops, all over h. Actually, that didn't quite work here because this isn't quite the identity that I need. So let's actually pull out a negative one here. So that's going to be negative sine x times, 1 minus cosine of h. I'm just flipping the signs then, right? And I'm actually going to go ahead and also at the same time split this apart like this into our two separate fractions before we got the common denominator. So we've done this before. This shouldn't make you panic at all. This is just showing like, hey, instead of combining, with the common denominator, let's write them separately. You can probably see where this is starting to go now. And then here, if these are both over h, I don't have to put the h over all of it. So I could go negative sine of x times 1 minus the cosine of h only over h here, because it's the same as like this being over 1, plus sine of h over h times the cosine of x over 1. Now, why is that important? Because remember, all of this is me taking the limit as h approaches 0, and if that's the case, this is going to be 0, so I'm going to get negative sine of x times 0, plus this one here is 1 times the cosine of x. This obviously just goes away, and so the answer to this is literally just cosine of x. And so what that means is that the derivative of sine x is cos x. All right, and rather than doing them both, you can probably get the idea that this one's going to be the exact same thing, but in the end, you're going to end up with, well, I guess you may think it's just sine. It's actually negative sine of x. So maybe I should do that to kind of show you and walk you through it. But honestly, you probably aren't going to need to do this proof, okay? But regardless, let's go ahead and show it here, just so that if you're having a hard time, you can still make sense of it. So this would be the cosine of x plus h minus the cosine of x all over h. And if we go up here so you can actually see it, this is where it's cos A or cos AB. So cos x cos h minus sine x sine h minus cos x. You can probably get the idea that once again I need to move that cosine over here so that I can pull it out. So let's do that all at the same time. Let's pull out that negative cosine of x. And it's on, let's just highlight that so you can see it. So I'm pulling it out of here and here. So if I pull out a negative cosine, this side's just going to be 1 minus, and then this is going to be our cosine of h minus sine x sine h. And once again, let's also write it with those two separate fractions. So just like before we got the common denominator and put them as a single one, like this. And remember again that this is the limit as h approaches 0, which means that this part here, actually no, we'll rewrite it one more time. Let's rewrite the step one more time. So that would be the limit as h approaches 0 of negative cos x times 1 minus cosine of h over h minus sine x technically over 1 times sine h over h. And remember, we can rewrite these as like 4 separate limits if we want to. It's like the limit of negative cos x times the limit as 1 minus cos h over h minus the limit as h approaches 0 of sine x times the limit as h approaches 0 of sine h over h, right? They're all like, we can rewrite limit on all those, but that's a lot of extra steps, so we're not going to do that. But we do know that the limit as h approaches 0 of this thing here is 0, which means I get negative cosine of x times 0 minus sine of x. And we know that the limit of sine h over h as h approaches 0 is 1. And so in the end, we get that that derivative, just like I said, was negative sine x. So almost the same as the other, except that this time it is indeed negative. So let's go write those down at the bottom. The derivative of sine is therefore cosine of x, and the derivative of cosine is therefore negative sine of x. Now, realistically, you're not going to go and like find these this way that we just did, but you are going to probably memorize these two and use them a lot. Okay? So let's do a few more examples, some of which are going to now have trig built into them. All right, this one here, it doesn't look like a polynomial, so our first step is to do that pre-calc algebra and make it do that. So 2x minus 1, I'm going to do the perfect square first because that's easier, because we know it's x squared plus 2 times the middle term plus the last term squared. Then I'm going to go ahead and distribute that all in, so 2x times everything gives me 2x cubed plus 4x squared plus 2x. Then I'm going to multiply the negative 1 into everything, so negative x squared minus 2x minus 1. Then I'm going to last combine my like terms, so 2x cubed. There's 4x squared and negative 1x squared, so plus 3x squared. Then I've got 2x and negative 2x. Oh, that's nice. That just goes away. And then minus 1. So now that I've got that, I can, of course, find my derivative. This is going to be 6x squared plus 6x. But if you notice, it gave me like when x equals 1, and that's because here we're being asked to find the equation of the tangent line. So that means I need that pot and sot that we've done before. So my pot is where I just plug negative 1 in. So it's negative 1 into the original equation, which let's see here. Here it's just going to be 0. So anything times 0 is 0. And then my sot, remember this one is where what I need to do is actually go and find like f prime of negative 1. So I'm going to plug negative 1 into this equation I just found here, which would literally be 6 minus 6, or 0. And so I'm going to get that y equals, or y minus 0 equals 0 times, and 0 times anything doesn't matter. And so this is the equation of that tangent line. All right, let's try it again, this time with some trig over here. I don't need to do anything to rewrite this. I can just go ahead and take the derivative. So the derivative of sine, we had said, was cosine. Now, don't get confused just because we changed this variable to a theta. The derivative of x is just 1. So the derivative of theta is just 1 as well. So this is minus 1. All right. So then if I'm looking for that pot and sot to now find the equation of that tangent line, the pot is pi over 2. And then I'm going to plug pi over 2 into this. And this is where it gets a little bit ugly. So cosine of pi over 2 is, oh no, it's not so, oh no, it's into the original, into sine. I was like, that's not so bad. No, it is. The sine of pi over 2 is 1. So this is literally going to be 4 minus pi over 2, which is a little bit ugly, but whatever. It's not that bad. And then my sot, this is where now I'm going to plug in the pi over 2 into this one, and that's a lot easier because cosine of pi over 2 is 0. 0 times 4 is still 0. Minus 1 is negative 1. So then I can go ahead and write in that equation. Now it is a little bit ugly, but don't worry about it. Just leave it in that ugly form. So 4 minus pi over 2. If you want, you could do a decimal, but I like just leaving it exact. Equals the slope times x minus our x coordinate. And so that would be the kind of ugly equation for our tangent line. All right, so on this next one, again, we're dealing with some trig here. There's nothing that I need to do to split anything, so I can just go straight to what that derivative is. The derivative of 2 theta is just 2. The derivative of cosine is negative sine, so this would be negative 3 sine theta. Now remember, this 3 is a coefficient. So I can just put it in front. The derivative, like, we don't need to worry about it. Okay, it just stays there. We can even pull it outside of taking the derivative if you want. But it's not going to change things. It's the variable that changes. All right, so now I can find my pot, which means I'm plugging in that pi into that original equation. So it's pi, and again, it's a little bit awkward here. It's going to be 2 pi plus, cosine of pi is -1 times 3, so -3. So we get kind of an ugly pot here, but it is still just a pot. And for our SOT, we're going to plug it into this bottom equation. So the sine of pi is 0, so it's just going to be 2 minus 0, or 2. And so now to write out that equation, again, you just write it out with that ugly number. So y minus the y coordinate, which is 2 pi minus 3, equals my slope times x minus the x coordinate, which is pi. So like I said, it's a little bit ugly. Don't worry about it. If that makes you uncomfortable, you can turn it into a decimal. All right, now this one, this actually isn't any trig, but we do need to rewrite this equation first of all. So this is the same as like 2x over x to the 3/2. And then, of course, I can simplify that because this would be 1 minus 3/2, and this would be 2x to the -1/2. All right, so h of x is therefore 2x to the -1/2, which means that h prime of x is going to be the -1/2 comes down. I get -1 times x. -1/2 minus 1 is -3/2. Then I need to go ahead and find those pot and SOT to get that tangent line. So I'm going to plug 2 into the original equation. So this is 2 and h of 2. h of 2 is going to be 4 over 2, 4, 8 square rooted, which is 2 root 2. And 4 over 2 is just going to be 2 on the top, so it'll be 2 over root 2. Or if you prefer, 2 root 2. Yeah, I mean, if we're American, then we would multiply this by root 2 over 2. And the bottom would just become a 2. The top is going to become 2 root 2. And so those will cancel, and you could just get square root 2 as well. Okay, or 2 over root 2. Doesn't matter. They're both the same. All right, now our SOT, let's hope it's a little bit easier. So now we're plugging it into our derivative, so this guy. So that's h prime of 2, which is going to be negative 2 to the -3/2. It's probably easier if you think of this as -1 over 2 to the 3/2. So 2 cubed is 8, square rooted is kind of exactly what we got before, actually. So it'd be -1 over 2 root 2. In this case, I would definitely leave it there. I would not bother to, yeah, I really don't think I would simplify that. But if you wanted, you could say, let's see, that would be multiplying it by root 2 over root 2. So we could get negative root 2 over 4. I don't know that that's any easier. So I'm going to leave it as that first one. So -1 over 2 root 2. Then I just write out my equation. So 1 minus square root of 2 equals my ugly slope, 1 over 2 square root 2, times x minus the x coordinate of 2. So again, a little bit ugly sometimes. If they really make you that uncomfortable, you can turn them into decimals. But I don't think it's that bad, really. All right, given the equation of a function, how might you determine the values at which the function has a horizontal tangent? Well, this means that the derivative equals 0, which means that it's going to be a relative max or relative min, right? So it's got that horizontal tangent line. At what values of x will this particular function have a horizontal tangent line? Well, that means that we call it f, so f prime of x is going to be equal to 3x squared plus 1. That's just me taking this derivative. And I want that thing to be equal to 0 so that it has that horizontal tangent line. So 3x squared plus 1. I'm going to move the 1 over. and divide by 3. So negative 1/3 equals x squared. And then I would take the derivative, or not the derivative, the square root. I cannot take the square root of this, right? This has no solution, basically, because I can't take the square root of negative. So like I said, no solution. And so therefore, when is this thing going to have a horizontal tangent? Never. It will never have a horizontal tangent. There is no place anywhere. All right, so now let's look at the next one and go back to our trig a little bit. At what values of theta at which the function this has a horizontal tangent on the interval from 0 to 2 pi. So let's first start by finding the derivative there. So f prime of theta is going to be 1, and the derivative of sine was cosine, so 1 plus cosine of theta. Now I want that to be equal to 0 to get that horizontal tangent. And then I'm going to move that 1 over, so negative 1 equals cosine of theta. And at that point, I mean, you could do it like this, wherever we take like the inverse of them, because this is like cos inverse of cosine of theta, and of course these cancel. And so theta is going to be the inverse of that, which